Can you hear me? Yeah, okay. First, I would like to thank the organizers for the opportunity to present my work here and to attend this very nice workshop. Today, I will talk about how an ultrastrongly coupled system can work as a single photon converter. Although this is a work that is still in progress, and we don't have all results, all desired results, but I hope I can show you some essence of this kind of device. That the basic operation is very simple. An incident photon is converted in another one with frequency, and we want to have some control of that frequency. This is the basic operation. But we can do more things, more interesting things with that. Okay, here we consider a quantum system that fits the simplest class of light-matter interaction. That is a dipolar coupling between a two-level quantum system and a quantized single-mode field. This kind of interaction is present in a plenty of quantum platforms and quantum technologies, ranging for quantum optics to condensed matter. Okay, the Hamiltonian that describes this the simplest interaction is the quantum RABI model, where omega c is the frequency of the cavity mode, omega q the transition frequency of the qubit, and G naught is the interaction that describes this dipolar coupling between them. Okay. For the sake of simplicity, let's assume the resonant case. Okay. When the cavity and the transition frequency of the qubit is equal. Okay. So for this case, we have this energy spectrum rescaled by G naught square over divided by omega. And we can classify this model in this way. So here we have the called perturbative ultrastrong coupling regime, okay, in which the interaction term is just a perturbation over the free energies. In this region, we can describe the system with the quantum Bloch-Seeger Hamiltonian that comprises the well-established James-Cummings model. At the other side, we have the perturbative deep strong coupling regime, in which the main driver of the system is now the interaction term. The free energies are just perturbations in it. Okay. And in the middle of these two regions, we have the non-perturbative ultra-strong coupling or the non-perturbative deep strong coupling, in which the characteristic features of these two regions coexist. Okay. In particular, we are interested in this region, mainly when we cross from the perturbative ultra-strong coupling to the non-perturbative ultra-strong coupling regime. Okay. Recently, a Japanese group have realized circuits, superconducting circuits that reach such a coupling strength. They can tune this coupling there from 0.7 to 1.3. Okay, so this is feasible experimentally. Okay, this is a zoom of that region. The colors represents a defined parity of the eigenstates. So the black lines have one parity, and the blue opposite one. Okay. This model has some selection rules in such a way that single photon transitions can be performed. So we can induce by single photons this transition 0 to 1 and 0 to 2, as well as from 1 to 3 and 2 from 2 to 3, but the from 0 to 3 and 1 to 2 are forbidden transition. Okay. So here we use 2 in order to induce such transitions. We will consider a weak linear coherent driving field on the cavity, which Hamiltonian is described by this one, or in which where epsilon is the strength, is the RABI frequency of the driving field, and it's weak. And we also consider that the systems are weakly coupled to a reservoir at 0 temperature. So the dynamics of the system is ruled by this Bloch-Hadfield master equation, in which the dissipations have this Lindblad form when the reservoir are Markovian. Okay, gamma is the transition rate from the K eigenstate to a lower one J, capital gamma. Gamma is the decay rate of the cavity C, or the qubit, when they don't interact. Delta is the detuning between the frequencies of these two eigenstates. Omega is the free frequency. And O is the operator that describes what kind is the interaction between each part of the system with their respective environment. Okay. So this equation describes the dynamics of the system. Okay. The proposal is we always drive the system in this transition, 0 to transition. So the frequency of the driving field is has always the frequency of this transition. So for the lower coupling region, that is for G not less smaller than this critical coupling, where there are a cross between these two eigenenergies, we can send a photon to the system, and if the system gets excited, the only way here is, because of the selection rules, the system transmit a photon with the same frequency. Okay, because this is only there's only one possibility here. Okay, for the higher coupling region, for G naught greater than this critical value, we can also send a photon in this transition, and we can also have the same frequency in the transmitted photon. However, in this case, we have another channel, another decay channel, because of the selection rules. We can also have a cascade transition here. The photon can, the system can transmit a photon in this frequency, and then in this frequency, and then in this frequency. So in this region, we have two decay channels. Or the system transmits one photon with the same frequency of the incident photon, or the system transmits 3 photons. Okay? And we are interested in this second situation, because here we can convert the frequency of the photon. All right? This is the gaps of the eigenenergies as a function of the coupling. So if we are able to tune the coupling between the system, we have some control over the frequency of the output photon. Okay. All right. So, but which is the more likely transition we have in a system, in a real experiment, for example. We have more direct transition or cascade transitions. So to understand that, we look to the transition rates between the eigenstates that are calculated in this way. Okay. Remember that OC characterizes the kind of interaction between each part of the system with its respective reservoir or environment. Okay. Here we will assume that the decay rate of the cavity is much greater than the decay rate of the qubit, because to ensure that the photons is transmitted by the cavity and not lost in the environment of the qubit. Okay. In the most paper of the literature, the authors use this kind of interaction between the cavity and its environment. The cavity couples with its environment via the momentum operator of the cavity. Okay. For example, these publications. For this case, if we calculate the transition rates, we see that the black dashed line is for the transition 2-0, that is the direct channel, okay? And in particular, this green line is the decay rate from the state 2 to state 3, okay? Because after the critical coupling, they invert. Okay, so here I write 3 to 2, but after the critical coupling is from 2 to 3. All right. So in this case, for this kind of interaction with the reservoir, we have that the direct transition is more likely. Okay, this occurs in more run of the experiment. So if we calculate the emission spectrum of the system, we see that. So here we have G0. So the lower coupling region, we have just the direct transition, direct transition, direct transition. So when we cross the critical coupling, we start seeing some small peaks here because they have lower probabilities than the direct transition, but they start to appear, but they are more unlikely here. Okay, so the conversion is not efficient in this case. All right. However, if we consider that the system couples to, if we consider that the cavity couples with its environment, with its position quadrature, we have a better thing. Here we can see that there's a range of coupling, that the transition rate from the state 2 to state 3 is bigger than the transition rate from the 2 to 0. Okay, so in this case, we have the role reversal. So again, in the lower coupling region, we have direct transition, but when we cross to the higher coupling region, we start to see the decay, the cascade decay channel, and it starts to dominate. Okay, so in this case, we can convert the incident photon more likely. So this is the basic operation. Of course, we can choose what frequency we want. For example, by coupling another open wave guide to the cavity, that we filter what photon we want. Okay, this is the basic operation. However, there are more interesting things, but I don't have the results yet. But future perspectives are these ones. For example, we have more control when qubits are tunable because we can control the output frequency so we can tune our output frequency with both controlling the coupling between cavity and qubit and controlling the qubit frequency of a superconducting circuit, for example. Okay, so we have a range that our quantum device operates. Another thing is, for example, consider n atoms instead of just a single one inside the cavity, because in this case we can decrease the value of this critical coupling. So in this way, we don't need a ultra strong coupling per atom to reach this critical value. This critical value is smaller. Another thing, it's as I said, this device has the basic operation of convert the frequency of the incident photon. Okay, because the optical properties of the system change dramatically when we cross this critical coupling. But we can use this kind of device, for example, to generate 2 photon pulses. Okay, how? If we couple, for example, another open waveguide to the cavity with frequency capital omega in this way, okay, in this dispersive way, so the cavity can couple to this transition and that transition, but dispersively. This kind of interaction provides this kind of effective dynamics. So we can virtually transfer this 2 photon process in a 2 photon in the open waveguide. So we send a photon to the system, and the system gives me a 2 photon pulse if we send a single photon pulse. Okay. And also, but this is our main goal. We are working in it. I don't have much results in this, but what I want is this: weakling not 1 or 2, but 3 additional open waveguides to the original device. This, in principle, could be used for the generation of heralded twin photons in a controllable way. Okay, but how? So in the same way, two open waveguides has the same frequency, and the other one with a different frequency. And in a 3 photon process, if this different open waveguide, if we measure a photon in this open waveguide, it heralds that a twin photons have been generated in the other one. But for this, we have to study the selection rules involving the momentum angular that we have not so much results in this. But this is our main goal. Of course, this quantum device seems to be very simple, just converting frequency, but we are interested in this kind of more complex process. So here we could have a controllable nonlinear crystal, for example. So I think I am the faster guy. So that's it. Thank you very much.